Hello students, let us discuss another important theory in order to explain the coordination compounds, that is crystal field theory. As we have already learned valence bond theory, it is based on the assumption that the bond between the metal ion and the ligand is purely covalent. But in the crystal field theory, it was based on the assumption that the metal ion and the ligand, the bond is actually purely electrostatic, or we can say ionic. So because of this, there are certain changes, as we have already discussed valence bond theory. So let us discuss the crystal field theory, which is based on the following assumption. So first, let us discuss the silent features of crystal field theory. In short, we are writing CFT for crystal field theory. The first silent feature is that the interaction between the metal ion and the ligand is electrostatic, or we can say ionic. As valence bond theory says, the bonding between the metal ion and the ligand is covalent, but here this theory says that it is electrostatic. That means it is not covalent, it is ionic. So according to crystal field theory, the ligands act like it is considered as a point charges. Like the ligands have negatively charges like Cl negative, Br negative. The negatively charged ligands act as negative point charges, and the ligands like neutral, which are neutral like NH3, H2O, these ligands act as dipoles. So according to this theory, the ligands are considered to be a point charges. That is, negative ligands are regarded as negative point charges, and the ligands with are neutral are regarded as dipoles. So according to this theory, the metal ion and the ligand having a electrostatic interaction. That means the metal ion M plus and the ligand, negatively charged ligand, like if I am writing X negative, this interaction, that is interaction between the metal ion and the negatively charged ligand, is an interaction that is called as ion-ion interaction. That is ion-ion interaction. But if the ligand are neutral, like water, ammonia, let I am representing as A. So the interaction between the metal ion and the ligand, which is neutral, that type of interaction is referred as ion dipole interaction. So according to this theory, the metal ion and the ligand is actually forming a electrostatic force of interaction between them. That is, if the ligand is negatively charged ligand, then the interaction is ion-ion interaction, and if the ligands are neutral like water, ammonia, which is polar in nature, so in that case the interaction is ion dipole interaction. So let us see what are the other silent features. That is, we will be discussing this for the two cases like octahedral complexes. So according to this theory, the 5 d orbitals in an isolated gaseous metal ion or the atom have same energy. It can be better represented through this energy level diagram, which is represented here. These are the orbitals, that is d orbitals, that is dxy, dyz, dzx, dx square y square and dz square. So the 5 d orbitals in the free metal ion. In the free metal ion, that means without ligand, that is we can write M plus. So the free metal ion in which the 5d orbitals have same energy. When you look at here, it's an energy level diagram. So these having same energy, that is the 5d orbital in the isolated gaseous metal ion or the atom have same energy. So we can say that they are in the state of degeneracy. That is called as, these are called as degenerate state. That means having the same energy. But this degeneracy is maintained if the spherically symmetrical field of negative charges surround the metal ion. It means that the degeneracy of the d orbital is maintained if the electrically, that is spherically symmetrical field of negative charges surround the central metal ion. But when the ligand, which is negatively field ligand, that is either an ion like Cl negative or the neutral ligand, when it approaches to this central metal ion, the degeneracy get disturbed. So their energy will slightly lift up. As you can see here, the energy of the 5d orbital is slightly lift up. That is due to the ligands, the approaching ligands. We can say that their energy will be slightly lift up. And because of the ligands which is approaching to the central metal ion, the degeneracy of d orbital get disturbed. Now it get splitted. You can see the d orbitals, now it is splitted into two sets. That is the T2g set and EG set. You can see here the 5d orbital, because of the ligands, this get splitted into two sets. The two sets are T2g and EG set. Now whichever orbitals are involved in T2g, that is dxy, dyz and dzx. So these orbitals of d is in the one set, that is called as T2g set. Now the energy of these three are same. So when you look at in the energy level diagram, these having same energy, that is you can see here the energy is same for the dxy, dyz and dzx, because their structure, their orientation is the lobes, that is the double dumbbell shape. Their double dumbbell is in between the axis. So they having lower energy in the case of octahedral complex, but the other set of d orbital, that is represented as EG set, having the orbitals dx square y square and dz square. So for these orbitals, the orientation of the dumbbell is along the axis. So these will experience us a little bit higher energy. These have the higher energy in compared to the dxy, yz and zx. That's why dx square y square and dz square, this set of orbitals will have greater energy in compared to the energy of dxy, yz and zx. So that means in this diagram we are splitting the 5 orbitals in such a way that for the case of octahedral complex, these have that is T2g set, that is dxy, yz and zx orbital have lower energy in compared to dx square y square and dz square orbitals. So in short, what we can say that the energy of EG set is slightly greater than the energy of T2g set of orbitals. So this is what called as a splitting of orbitals, that is splitting of d orbital is taking place, that is due to the influence of the ligands, which can be negatively charged ligand or can be neutral. Now when you look at here, the separation of energy, that means the energy gap between these two sets is represented by delta naught. This energy separation is denoted by delta naught, which is represented here in this diagram, and here subscript O is referring for the octahedral. That is why it is written as delta O. Here the O is representing for octahedral. So the energy separation is represented by delta naught. This energy separation is called as crystal field splitting. And when you look at here, the energy of EG set is slightly increased and the energy of T2G set is slightly decreased. So how much it is increased? Thus the energy of two orbitals of EG, that is dx square y square and dz square, will be increased by 3 by 5 of delta 0, and that the energy of dxy, yz and zx, that is the three orbitals of T2G, its energy is decreased. How much is decreased? That is 2 by 5 delta 0. It is given in this figure. So what we can say that in the central metal ion, the d orbitals, that is 5d orbitals, are in the degenerate state. That means all these have same energy. But due to the influence of the central metal ion of the ligand, due to the influence of the ligand, their energy will be slightly lift up. That is the average energy of d orbitals in the spherical crystal field. But due to the repulsion experienced by the orbital electrons with the electrons of the ligand, there will be a splitting of d orbitals, and the splitting is taking place in two sets, that is the orbitals like dxy, yz and zx. Their energy gets slightly decreased, that is 2 by 5 of delta 0, and the energy of the two orbitals, that is dx square y square and dz square, which are represented as EG set, their energy slightly increased, that is by 3 by 5 delta 0. So this splitting is called as crystal field splitting. So here the splitting of d orbital is taking place, that is called as crystal field splitting. And the energy gap between the two sets is represented by delta 0, that is called as crystal field splitting energy, that is represented by delta 0. So for doing the problems, it is better to make this diagram in this way, that is the d orbitals. These are the d orbitals. Here the energy of these 5 d orbitals are same. That's why you have to make all the 5 boxes, that is the orbitals, in same line as it is seen here. All have same energy. So that means when you are making this diagram, first you have to make the 5d orbitals in the same line, which shows that they have same energy, that is in the degenerate state. But due to the influence of the central metal ion, because of the influence of the ligand, there is a splitting of d orbital into the two set, that is the T2G set. Now this is T2G set, which have lower energy, and the EG set have a little bit greater energy. So you have to make the 3 boxes down and the 2 boxes you have to make up. So it is very important to remember this, which one will come down. That is the 3 boxes, that is T2G set you have to make down and EG set you have to make up. So here this splitting energy, crystal field splitting energy, it is represented here, that is delta. For solving the problem, it is important to learn this diagram instead of this. Now let us take the case of a tetrahedral complex. In the case of tetrahedral complex, here also there is a degeneracy for the central metal ion which get disturbed due to the effect of ligands. Here also splitting takes place. The d orbitals undergo splitting, but here the splitting, in this case it is observed because of the studies which is done, it is observed that the orbitals like dx square y square and dz square have lower energy, and the orbitals like dxy, yz and dzx have a slightly greater energy. So their energy separation is represented by delta T. Now here the subscript T is representing for tetrahedral complex. As we have learned, in octahedral complex it is represented by delta naught, but in tetrahedral complex will represent it with delta T. So the crystal field splitting energy is represented here delta T. Now how much is there is an increase in the energy of dxy, yz and dzx, that is 2 by 5 of delta T. And here in the case of dx square y square and dz square, the energy of it is decreased. How much it is decreased? That is 3 by 5 of delta T. What is delta T? Is this? It is a crystal field splitting energy in the case of tetrahedral complexes. So this is for the diagram for the case of tetrahedral complex. Now when you compare this diagram with the diagram for octahedral complex, it is clear that here you are making the 3 boxes down and 2 boxes up. That is clear from this diagram. For the case of octahedral complex, you will be making 3 boxes down and 2 boxes up, because the energy of dx, y, yz and zx are lower, and the energy of dx square, y square and z square is greater. But in the case of tetrahedral complex, when you are making the diagram, it is made in this way. Here the 3 boxes are made up and the 2 boxes are made down because of the energy variation here. So for solving the problem, it is better to make this diagram. So instead of making this diagram, it is better to make this diagram. So when you compare the two complexes, that is octahedral and tetrahedral complex, it is clear that for the case of tetrahedral complex, the E set, here it is not used G, it is only used E. E set, and it is represented as T2 set. So E set have a lower energy, T2 set have greater energy. But in the case of octahedral complex, the T2G set is having a lower energy, but the EG set have greater energy. So in simple words, how we can learn this very easily? For octahedral, make the 3 boxes down. So automatically if the 3 boxes are down, 2 boxes will be up. But tetrahedral complex, just make the reverse of it. That is 3 boxes you made down, here 2 boxes are made down. So it is very easy to learn when you learn this in this way. Now here the splitting is actually taking place, but depending upon the ligand, the splitting can be greater splitting or lesser splitting. So the delta 0 value for the case of weak field ligand, the delta 0 value is less. That means the splitting is less, but in the strong field the splitting is greater. That is, it is greater than the pairing energy. P is the pairing energy. So when you look at here in the case of octahedral complexes, the d orbital which is splitted into T2G set and EG set, and this splitting is represented, that is delta 0. This crystal field splitting energy is represented by delta 0. That is in the case of the strong field, and in the case of weak field this splitting is less. So when you compare these two cases, Here, this is the case for strong field. You can see there is greater splitting. That means there is the greater value of delta 0. But in the case of the weak field, this splitting is actually less splitting. That means the energy gap, that is this energy gap which is represented by delta 0 is less. So that means here the splitting is quite lesser when there is a weak field ligands, but the splitting is greater when there is a strong field ligands. So what we can compare from these two, that is when there is a strong field ligand, there will be a greater energy differences between the two sets, that is T2G and EG set of orbital. There is a greater energy difference because delta 0 is greater here. But in the case of if the ligand are weak field ligand, so in that case this splitting is lesser. That means the delta 0 value is less. So there is less energy gap between the T2G set and EG set. So depending upon this concept only, we are getting some of the complexes are paired. That means in which pairing is taking place, and in some complexes there is no pairing. So that is we will be explaining with some particular examples. But in the tetrahedral complex, consequently, the orbital splitting energies are not sufficiently large for forcing the pairing, and therefore low spin configurations are rarely observed. It is one of the most important reasoning type of question, that why the tetrahedral complexes does not shows low spin complexes. That is, either it is asked in this way, why the tetrahedral complexes show rarely the low spin configuration, because of the reason as the orbital splitting energies are not sufficiently large here. That means this splitting is not large in the case of tetrahedral complexes. So there is the pairing is not much possibility in the case of tetrahedral complex. So it is one of the most important question. Usually the questions arises, that is a reasoning question on this part. What is the crystal field strength? So this splitting is depending upon it depends upon the nature of the ligand, and it depends upon the oxidation state of the central metal ion, that is its charge. So when we talk about the nature of the ligand, as I told you, when there is a strong field ligand like CO, CN, ammonia, in such a case the splitting is greater. That means the delta 0 value is greater when there is a strong field ligand. But the weak field ligand, if we have like a Br negative, Cl negative, in such cases the splitting is less. That is delta 0 value is less comparatively when there is a weak field ligand. So the crystal field splitting depends upon the nature of the ligand. So greater will be the strength of the ligand, that is strong field ligand causes greater splitting, and the weak field ligand will causes less splitting. So in general, the ligands are arranged in a series in order of increasing the field strength. This series is called as Spectrochemical Series. It is given here. This is the Spectrochemical Series in which the ligands are arranged in a series of increasing field strength. You can see which is on this extreme side. These are having stronger field ligands, and these are the weaker field ligands. So such a series is termed as a spectrochemical series. It is actually an experimentally determined series based on the absorption of light by the complexes with different ligand. So now it is not necessary why it is stronger, why it is weaker to study. That is in the higher studies. So this actually experimentally determined series is actually the spectrochemical series for the ligands. Next is the oxidation state of the central metal ion. If greater will be the oxidation state of the central metal ion, there will be greater delta 0. So delta 0 value depend upon the oxidation state of central metal ion. So when you compare the M3 plus and M2 plus, M3 plus it have greater oxidation state, or we can say the charge. So it have a greater delta 0 value, that is greater splitting is taking place. Now let us take a particular example to make the filling of electrons in the d orbitals, and we have to fill the electrons in the T2G and EG set. So for this we will be taking this example, that is CONH363 positive. The same example we have discussed the hybridization in the valence bond theory. Here for filling the electrons we have to use all the rules which we used in the filling of electron in the orbitals, that is Hund's rule, Pauli exclusion principle and the upper principle. We have to follow these three rules. As we have learned in the 11th standard, we have to follow the three rules in filling of electrons in this. So first of all, we'll be doing for this example. Here the central metal ion is CO3 plus. When you find it out by X method, the central metal ion is CO3 plus. So let us find out how many electrons are there in the D, that is 6 electrons are there in D. Now we have to fill the electrons in the D. So in the degenerate state, how we make the filling of electron? Like this: 1, 2, 3, 4, 5. And where will be the 6th electron? 6th electron will be in the first box. Now this is the case when you are filling the electron in the degenerate state of D. Now the same electron we have to fill in the T2G set and EG set. But look at the field here. That is strong field ligand is there in this. So definitely the delta 0 value will be greater. Before that you have to look at here, it is the octahedral complex because coordination number is 6. So you have to make T2G down and EG up. Now in this case we can say that there are 6 electrons and the delta 0 value, that is actually delta 0 value is greater because of the strong field ligand. Because here there is much energy difference between. So electron, it is not easy to jump to higher. So first here the pairing is taking place because the delta 0, that is it is greater than the pairing energy. So here there is a more possibility of pairing. So that we have to do here. So now we will be doing the filling of 6 electron. That is first electron here, second here, third here. Now where the fourth electron will goes? Does it goes in this? That is in the dx square, y square, dz square. Is it moves there? No. Because the delta 0 value is greater. That means much energy is required to move to the upper d orbital. So in that case, it will be start pairing here because the pairing energy is lesser. So the next one will be pairing here. So the fourth electron will be here, fifth electron will be here, and sixth electron will be here. So we can say that this complex is dimagnetic because all the electrons are paired. When you look at here, all the electrons are paired because you can see here the pairing is taking place because of the strong field ligand. So when you compare this with the VBT model, that is hybridization, we have done for the same example. In that also you can see that that is also diamagnetic, and the 6 electrons which is present in the D are get paired. So here the pairing is explained on the basis of splitting of D orbital. So now when you are writing the configuration according to crystal field theory, what will be the configuration here? Because this is a T2G set and there are 6 electrons are there in T2G. So its configuration is T2G6. And what about EG? How many electrons are there in EG? There is no electron. So EG 0. So that is the configuration for this example, that is T2G6 EG 0. In exams you will be getting question on this one. Write down the configuration, that is D orbital configuration for this particular complex. So what you need to do, you have to make the splitting of D orbital diagram which is shown here, and you have to fill the electron how I done here. So then you will be getting the configuration in this way. Now we'll be discussing the next example, that is COF6 3 minus. Here the central metal ion is CO3 plus. CO3 plus, that is having 6 electron in the D. So that is D6. Now we have to fill the electron in the degenerate D orbitals, that is 1 here, 2nd here, 3rd, 4th, 5th, and this is the 6th electron. Now because here there is a splitting of D orbital into T2G and EG set. Now why we have made T2G down? Because the coordination number is 6 here. That's why octahedral complex. So we have to make T2G down and EG up. And here when you look at here, the ligand is actually a weak field ligand, that is F is actually the weak field ligand. So here the splitting is actually, the splitting between these two will be less, that is the delta 0 value is lesser in compared to pairing energy. So that means here the possibility of pairing is less because the pairing energy is greater here, and delta 0 is smaller, means easily the electron can move into the above set. So now we'll be doing the filling of these orbital, that is D2G set and EG set. Here 6 number of electron as it is made here, these electrons we have to fill in this. So we'll start from the lowest energy orbital here. In the case of T2G and EG set have lower energy. So we'll be starting from down because it is an energy level diagram. So we have to start from the lower energy as the above principle says. So the first electron will be making here, that is the first electron, second electron, third electron. Now where the fourth electron we have to make, because delta 0 value is lesser, that means the energy gap between these two is lesser. So we can make the fourth electron here, then the fifth electron here. Now we can see that all the boxes are singly occupied, that means all the D orbitals are singly occupied. So according to the rule says that once all are singly occupied, then only the pairing begins. Now we have to start the pairing. Now where the next electron will take the position, that is here, this. So the sixth electron will be in this orbital, that is in the T2G set, that is from lower energy. So the pairing we have to start here. Now only 6 electrons are there, which we have done it here. Now we need to make the configuration. We need to write the configuration. So we will be writing the configuration, that is the configuration we are writing T2G set. T2G set having how many number of electrons here? T2G set, when you look at here, there are 4 number of electrons are there in T2G set. Therefore T2G4 will be writing. Then EG set, how many number of electrons are there in EG? 2. So that is 4. 4 plus 2, that is what we are getting, the 6 electron. So here the configuration for this complex is T2G4Eg2. That means how many number of unpaired electrons are present when you look at here. How many number of unpaired electrons are there? That is this electron is unpaired, this one is unpaired, and here also 2 unpaired electrons are there. So total 4 unpaired electrons are there, that is n is equal to 4. So this is what gives the value of unpaired electron is equal to 4, that it is paramagnetic. So when you compare this with the same complex which we have discussed in hybridization, there also you are getting the number of unpaired electron is equal to 4. So that means when you compare the complexes, when you compare it with the CFT model or the valence bond theory model, will be getting the same result, that is it is paramagnetic, and the unpaired electron here it is 4. That is also we got the number of unpaired electron 4, as we have discussed this example by VBT method. And when we have explained this with the CFT method, then we also got the same result, n equal to 4. So that is the similarity we are getting in both the cases, but the way of approach is quite different. So this is what about the crystal field theory. So the problems related to this one can be discussed in the next session. So this is all about this video. Have a nice day.